You can run Doom inside a PowerPoint file. Not as an embedded video, not as a screen recording, actually playable, running on the logic of PowerPoint itself. And here's the twist, it's not a hack. It's math. The presentation tool your manager uses to bore you in meetings is, in a strict mathematical sense, a full programming language. Anything a computer can compute, PowerPoint can compute. And once you understand why, you'll start seeing this same hidden power in the strangest places. To get there, we need to talk about one of the deepest ideas in computer science. It's called Turing completeness. And it's weirder, and more common, than almost anyone realizes. Back in 1936, a mathematician named Alan Turing imagined the simplest possible machine. Just a strip of tape divided into cells, a head that could read and write symbols, and a tiny set of rules telling it what to do next. That's it. No keyboard, no screen, no apps. Just read a symbol, maybe change it, move left or right, and repeat. It sounds almost insultingly basic. But Turing proved something astonishing. That absurdly simple machine could compute anything that is computable at all. Any calculation, any algorithm, any program that any computer could ever run, this little tape machine could do it too, given enough time and tape. So here's the definition that matters. A system is Turing complete if it can simulate that machine. If it can do everything Turing's machine can do, then it can, in principle, compute anything. And it turns out you don't need much to clear that bar. You basically need 3 ingredients. 1. The ability to read and write some kind of state, a memory you can change. 2. Conditional logic, the ability to do different things based on that state. And 3. The ability to loop or repeat until a condition is met. Memory, decisions, and repetition. That's the whole recipe. Any system that has all 3, in a flexible enough way, is Turing complete. And that's a shockingly low bar to trip over by accident. Which brings us back to PowerPoint. Because it turns out PowerPoint has a feature that quietly checks every box. That feature is animation triggers. You can set a shape so that when you click it, another shape moves, appears, or disappears. And crucially, one shape moving can trigger the next animation automatically, in a chain. A researcher named Tom Wildenhain proved this rigorously in a gloriously deadpan academic paper. He showed that PowerPoint's shapes act as memory, the trigger conditions act as logic, and the chaining acts as looping. He literally built a working Turing machine out of PowerPoint slides. Shapes representing the tape, arrows representing rules, all firing off each other with click triggers. No macros, no code, no VBA scripting. Just the animation engine doing what it was designed to do. And since a Turing machine can compute anything, PowerPoint can too. Which is exactly why someone was later able to get Doom running inside it. Slow, absurd, but real. The engine never intended for programming was secretly a computer all along. Now here's where it gets fun. Once you know the recipe, memory, logic, loops, you start spotting Turing completeness hiding everywhere. And the examples get ridiculous. Take Microsoft Excel. Most people think of it as a glorified calculator. But in 2021, Microsoft added lambda functions, letting formulas call themselves recursively. That gave spreadsheets loops. And people immediately proved Excel was Turing complete by building working computers inside a grid of cells. That means, in theory, any program on your laptop could be rewritten as an Excel spreadsheet. It would be monstrously slow and impossible to maintain, but mathematically, it's just as powerful as any programming language on Earth. Then there's Minecraft. Inside the game, redstone acts like electrical wiring. Players use it to build logic gates, the same and, or, and not gates that make up real computer chips. People have built fully functioning CPUs inside Minecraft. Calculators, memory banks, even a machine running a scaled-down version of Minecraft inside Minecraft. It's Turing complete because redstone gives you all three ingredients, and endless patience does the rest. And here's my favorite. The card game Magic, the Gathering. Not the video game, the physical cardboard game. Researchers proved that with a specific legal arrangement of cards, the game state itself simulates a Turing machine. The cards on the table become the tape, the rules of combat become the logic, and forced sequences of play become the loops. That leads to a genuinely mind-bending conclusion. There are magic games where determining who eventually wins is mathematically undecidable. No algorithm can always answer it, because the game is, itself, a computer. So why does any of this matter beyond party trivia? Because Turing completeness has a dark side, and it's one every developer should respect. If a system is powerful enough to compute anything, it's also powerful enough to be unpredictable. You can't always tell in advance whether a program will finish or loop forever. That's Turing's famous halting problem, and it's provably unsolvable. This is why config files, template languages, and smart contracts sometimes deliberately avoid being Turing complete. If you give a configuration format loops and recursion, an innocent-looking file can hang your entire system or open a security hole. It's a real design trade-off. More power means more expressiveness, but also less predictability and more ways to break. Sometimes the smartest engineering decision is to make your system deliberately weaker. So the next time you're stuck in a soul-crushing slideshow, remember, that same tool could theoretically run Doom, simulate a computer, or compute anything in the universe. Turing completeness isn't some rare, exotic property. It's a low bar that reality keeps tripping over, in spreadsheets, in games, in cardboard, in slides. The line between a tool and a programming language is thinner than you think. Sometimes it's just 3 ingredients away.